Today we are going to learn about mastering random sampling with numpy. You will learn how to use numpy for random sampling, a critical skill for data analysis, simulations, and machine learning tasks.
Random sampling is a fundamental concept in data science, used to select a subset of data from a larger dataset. It is crucial for ensuring that the sample represents the population, reducing bias, and enhancing the quality of analysis. In this video, we will explore how numpy, a powerful Python library, facilitates random sampling. You'll learn about different sampling methods, how to implement them using numpy, and apply these techniques in real-world scenarios. By the end of this video, you'll have the skills to perform random sampling efficiently and effectively in your data science projects. Before diving into numpy, it's essential to understand the basics of random sampling. Random sampling involves selecting a subset of individuals from a larger population, ensuring that every individual has an equal chance of being chosen. This technique is crucial in data analysis for obtaining unbiased samples, leading to more accurate results. There are various types of random sampling, including simple random sampling, systematic sampling, and stratified sampling. Each type serves different purposes, depending on the data structure and the analysis goals. In simulations, random sampling helps mimic real-world processes, making it a vital tool in predictive modeling. Machine learning models often require diverse datasets to generalize well, making random sampling an indispensable step in data preparation. Understanding these principles lays the groundwork for effectively using numpy in your sampling tasks.
Numpy offers the function numpy.random.choice, a versatile tool for random sampling. This function allows you to choose random samples from a given array or list. Its syntax is straightforward. numpy.random.choice a, size equals none, replace equals true, p equals none. Here, a is the array you are sampling from, size is the number of samples, replace determines whether sampling is with or without replacement, and p is the probability distribution. Sampling without replacement is particularly useful when you want unique samples, ensuring that each item is selected only once. Let's look at an example. Suppose you have an array of numbers representing customer IDs, and you want to randomly select 10 customers for a survey. Using numpy.random.choice, you can easily achieve this by setting replace equals false. This method is efficient and integrates seamlessly with other numpy functions, making it a powerful tool for data scientists. The ability to specify probabilities for each element adds an extra layer of flexibility, allowing for weighted sampling based on your specific requirements.
Stratified sampling is a method that ensures each subgroup, or stratum, within a population is adequately represented in the sample. This technique is particularly useful when dealing with heterogeneous populations where certain characteristics vary significantly across subgroups. In numpy, stratified sampling can be implemented by first dividing the population into strata based on specific attributes, such as age, income, or education level. Once the strata are defined, you can use numpy.random.choice to sample from each stratum proportionally. This approach ensures that the sample mirrors the population's diversity, reducing bias and improving the accuracy of your analysis. For instance, if you're analyzing customer satisfaction across different age groups, stratified sampling ensures that each age group is represented according to its prevalence in the overall population. numpy's flexibility allows you to automate this process, making it efficient even for large datasets. By maintaining the balance of sample proportions, stratified sampling enhances the validity of your findings, providing a more reliable basis for decision-making.
Sampling with replacement is a technique where selected samples are returned to the population, allowing them to be chosen more than once. This method is particularly useful in simulations, where you might need to model processes that involve repeated selections, such as bootstrapping. In numpy, this is easily achieved using numpy.random.choice with the parameter replace equals true. Consider a scenario where you want to simulate customer purchase behavior. Sampling with replacement allows you to mimic real-world scenarios where customers can make multiple purchases. This approach is also valuable in creating datasets for machine learning, where the same data point might need to appear multiple times to achieve a desired distribution. However, it's crucial to be mindful of the impact on sample diversity, as repeated selections can lead to overrepresentation of certain elements. To mitigate this, you can use probability distributions to guide the sampling process, ensuring a balanced representation that aligns with your analysis goals. numpy's efficient handling of large arrays makes this process seamless, providing robust support for complex sampling tasks. Working with large datasets poses significant challenges, particularly in terms of memory usage and computational efficiency. numpy, with its optimized performance and array processing capabilities, offers robust solutions for efficient sampling from large datasets. One key technique is to use memory-efficient data structures, such as numpy arrays, which consume less memory compared to traditional Python lists. numpy's built-in functions are designed to handle large data volumes with minimal overhead, making it possible to perform random sampling without exhausting system resources. When sampling from large datasets, it's important to consider strategies such as downsampling and chunking, where the dataset is divided into smaller, manageable segments. This approach not only optimizes memory usage but also enhances processing speed, allowing you to focus on specific data segments without compromising the overall analysis quality. NumPy's ability to integrate seamlessly with other data processing libraries, like Pandas, further extends its capabilities, offering a comprehensive toolkit for tackling large-scale data challenges. By leveraging NumPy's efficiency, you can ensure that your sampling processes are both effective and scalable. Random sampling is a cornerstone of various real-world applications, playing a critical role in fields ranging from business analytics to scientific research. In business, random sampling is used to analyze customer behavior, forecast sales, and develop targeted marketing strategies. By selecting representative samples, businesses can gain insights into market trends and consumer preferences, enabling data-driven decision-making. In scientific research, random sampling is essential for conducting experiments and surveys, ensuring that findings are statistically significant and generalizable to the broader population. Financial modeling also relies heavily on random sampling to simulate market scenarios and assess risk, providing valuable insights for investment strategies. Marketing strategies benefit from random sampling by identifying target demographics and tailoring campaigns to specific audience segments. In healthcare, random sampling aids in epidemiological studies and clinical trials, helping researchers understand disease patterns and treatment efficacy. By mastering random sampling techniques with NumPy, you can effectively apply these skills across diverse domains, enhancing the quality and reliability of your analyses. While NumPy is a powerful tool for random sampling, it's essential to understand how it compares with other Python libraries like Pandas, SciPy, and scikit-learn. Each library has its unique strengths and use cases. Pandas, known for its data manipulation capabilities, offers sampling functions that complement NumPy's array processing. However, NumPy's performance is superior for numerical computations, making it the preferred choice for large-scale sampling tasks. SciPy, with its extensive scientific computing functions, also provides sampling capabilities, but NumPy's simplicity and speed often make it more accessible for everyday tasks. Scikit-learn, a library for machine learning, integrates seamlessly with NumPy, using its arrays for data processing and model fitting. When choosing a library, consider factors like dataset size, computational requirements, and specific use case scenarios. NumPy's versatility and efficiency make it a go-to choice for random sampling, but understanding the strengths of other libraries allows you to leverage the best tools for your data science projects, ensuring optimal performance and outcomes.
Mastering random sampling involves not only knowing how to implement techniques but also understanding best practices and avoiding common pitfalls. One crucial aspect is determining the appropriate sample size, which should be large enough to represent the population accurately but not so large that it becomes impractical to analyze. Avoiding selection bias is another key consideration, ensuring that every member of the population has an equal chance of being selected. This can be achieved through careful design and implementation of sampling techniques. Maintaining data integrity is essential, particularly when dealing with sensitive information, requiring robust data handling practices. Balancing computational resources is also important, especially when working with large datasets, to prevent system overloads and ensure smooth processing. Finally, troubleshooting common issues, such as unexpected sampling results or performance bottlenecks, requires a systematic approach to identify and resolve underlying problems. By adhering to these best practices and being aware of potential pitfalls, you can enhance the accuracy and reliability of your random sampling processes, leading to more insightful analyses and better informed decision-making.
In conclusion, mastering random sampling with NumPy is a valuable skill for any data scientist. We've explored the fundamentals of random sampling, delved into advanced techniques like stratified sampling, and highlighted the importance of NumPy's efficient handling of large datasets. The practical applications of these skills span numerous domains, from business analytics to scientific research, providing a robust foundation for data-driven decision-making. As you apply these techniques, remember that practice is key to mastering them. Experiment with different sampling methods, explore real-world datasets, and continue to expand your knowledge. Additional resources are available to deepen your understanding and keep you updated on the latest advancements in data science. By leveraging NumPy's powerful functionalities, you can enhance your analytical capabilities and contribute to impactful, data-driven insights.